Assalamualaikum viewers, please like, share and subscribe this channel. Links of PDF files used in this video are given in description. So this lecture is about how to determine unknown concentration of a solution by using UV-Visible Spectrophotometer. So we are using Dynamica HALO DB-20 UV-Visible double beam spectrophotometer for this experiment, and this is the main model of this instrument, and this is the main screen from which we operate all the processes, and this is the sample container which is covered. If we see from the top, so this is the main screen and these are all buttons from which we operate the instrument, and similarly this screen has been uh, explained here with zoom, and this is the Dynamica model which we are currently using. Now if we see the screen, then we have various types of buttons like the main menu button, start stop, wavelength start stop of the analysis button, and this is the enter button in order to enter in some menu. From here we go left, right, top, down. This is the autozero button, and these are the numerical numbers, and this is the clear or return button. Now as we make a electrical connection and on the instrument, then first of all the screen appears is this main menu, and this main menu contains various further menus like photometry, wavelength scan, time scan, multiple wavelength, file manager, calibration and test menu. If we are starting our day and making the instrument on first time, then first of all we will do a calibration, and when we will enter in this menu, then we will do a wavelength calibration. However, it is not necessary to make wavelength calibration every time, but if you are making the instrument on after a 2 or 3 or even after a week, then sometimes we do the calibration. Otherwise there is no need for doing the calibration. So as we on the instrument, we mainly see the main menu, and in this main menu for this current experiment we will select the option of photometry. Next we will place our reference and our sample in cuvettes, and then we will place these cuvettes inside the instrument. So as this is a double beam spectrophotometer, so there are two cuvettes that will be placed. The place which is away from your side is for the reference, and whereas the place which is towards your side, that is place for the sample. So here we will place a reference cuvette, and here we will place the sample cuvette. If you see here, these are two small holes, and from these holes light is actually coming from the light source. So light travels from left to right, and similarly from this direction to this direction. So this is the sample compartment, and if you note that inside it is all black, so in order to avoid any stray light, the black material will absorb that stray light, and we will only observe the light that is coming from the light source. So this is the sample compartment, and it is covered with this cover. So we slide down this cover to close the instrument to close the sample compartment, and then analysis will be performed in this closed position. So here in this slide you will see that we have placed the reference cuvette at this position and our sample position at this position, and for this current experiment we are using KMnO4 in order to find the unknown concentration, and therefore we will also make standard solutions of KMnO4. So from these holes light is coming from left to right, and here in this position there has been placed detectors. These detectors detect the light which reach the detector after particular absorbance. So in order to determine the unknown concentration, we will select this menu which is of photometry. However, before start of unknown concentration, we will perform a wavelength scan, and this wavelength scan is used in order to find the lambda max. So in order to know how to determine the lambda max of an unknown solution, so if you see from my previous lectures, the link has been shared in the upper right corner. So if we see from that video, that from by using wavelength scan we first determine the lambda max of a solution, and after then we will perform the unknown concentration, and in order to know the unknown concentration we select the menu of photometry. So as we select the menu of photometry by pressing the enter button on the keypad, then further menus will be opened, and if you see here, first of all this menu is called as a parameter setup. So if we enter in this parameter setup by pressing the enter button on the numerical pad, we will see here two options. First of all, we will select this option, and this option is for measurement, and here we will change the measurement to concentration. Actually, when you select this menu, so here in the bottom there appears three options. Number one option is for absorption, number two is for concentration, and number three is for transmittance. So in the previous experiment of lambda max we have placed here the menu of absorption, but in this particular we will select the menu of concentration here. So in after setting this, we will press down and press enter, and we will then edit the wavelength, and this wavelength is used for the lambda max value. And if you see here, in the previous experiment we have determined the lambda max of KMnO4, which is around 524. So that value will be placed here, and in order to set this value we have actually performed the experiment of how to determine the wavelength or lambda max of a solution. After the parameter setup, we will scroll down and we'll go to the second menu, which is of sample setup. We will press enter, and then we will enter in further menus. First option is for name. Here you can edit the name of your sample. This is the path length, and we will stick to the 10 because the width of our cuvette, that is this length, is of 10 millimeter. So we will keep it as it is. Unit label we can change it, but we are making solutions or using solutions in ppm, so it will remain same. And sample number, the analysis can be performed from any number, but we will start in this particular analysis from 1, so the starting number is 1. After sample setup, we will enter into third menu, which is very important, and this menu is called a curve setup. We will press enter, and we will enter in this menu. So here in the first bar we will see that either this analysis will be first order, second order, or third order. So we will use it as first order because absorption is directly proportional to concentration according to Beer's law. So we will keep it as first order. Second is the number of standards, how many number of standards we are using. In this particular instrument we can use standards up to 20, but for this particular analysis, in order to save the time, we will use only 5 standards plus 1 blank solution in order to get the value of 0 ppm. So we are using the 6 standards in this particular analysis. However, as many standards are there, then the calibration line will be more robust. So it is always good to use always a greater number of standards. And if the use of the advantage of greater number of standard is that if 1 or 2 points are out of the line, then we can ignore those points, and the calibration line will be not disturbed easily. However, if we are using less number of standards, we will be having a less number of points, and if 1 or 2 points deviate from the linearity, then overall curve will be disturbed. So that is why we are always prefer to use greater number of standards, and in this particular instrument we can use 20 standards. After then we will enter into this menu which is of curve data, and this is very important. When we open the curve data or the curve setup, and in this we will see the curve data points. So here if you see here that already 6 standards have been selected, but if we change the standards in the previous menu, then that standard will appear here. Now correspond to each standard there are concentration values. Now we have to put these concentrations manually, like these are the concentrations of standards, so we have to input the data for the concentration of standard solutions. In this particular analysis we have used the standards from 1, 2, 3, 4 and 5 ppm, but if you have prepared standard solutions in 10, 20, 30, 40, 50, or if 100, 200, 300, so here you see you can enter any value from 0 to 9099. So there is no restriction in that. However, in this particular analysis we are using the concentration of standards which is ranging from 1 to 5 ppm, and the first standard is will be 0 ppm, which is for the blank. So here we are actually inputting the data of the concentrations of standards, and we have to give this data to the instrument in order to draw the calibration curve of the standard solutions. So up till this point all the settings have been done, and after then we will move towards the forward screen. In order to move to the forward screen, which is actually the real screen of the analysis, we can opt two ways. Either we will scroll down and after then we will enter into forward menu, or directly we can press the 0 button here, and when we will press that button we will automatically go to the forward screen. And if we say here, this is the main analysis window after pressing the forward screen. Here if you see here, in this point there will be standards, in this line there will be the value of absorption, and in this line there will be the corresponding value of the concentration of that standard. We have used actually in this particular analysis the 6 standards. So first is the blank, second, third, fourth, fifth and sixth. After the analysis has been performed, the instrument will automatically draw a calibration curve or calibration line. So if you see here, we have placed the first standard in the sample cuvette, and then that cuvette has been placed in the sample compartment in the sample cuvette or towards our side position, whereas the reference will be placed in the away position. And after second standard we will replace this cuvette with the new cuvette containing the standard number 2, 3, 4, 5, 6, and in this way the analysis will be performed, and here we will get the values of absorption, and here we will get the values of the concentration. So if you see here, it has been written that insert standard and press start to measure or return to the end. So in order to start the analysis, we will press the start button on the instrument, which I have shown you people earlier. So when we will press the start button, the instantaneously the absorption of the that particular sample will be noted, and its corresponding concentration will be displayed here, as we have already input the data of the concentration of the corresponding standard. However, one thing must be important, that for the very first sample before the start of this analysis, which is started from this button, whenever we will place our first standard, which is actually the blank solution, so in order to have a good value, we will press 1 or 2 times the button of autozero. Autozero means that the instrument has ignored all the straight light, and the value for the blank solution, if it absorbs some light, then it will be calculated as 0. So in order to have a baseline of 0 value, we will press this button one or two times, and then we will get the absorption of zero value and concentration of zero value for our first standard, which is actually the blank solution. So that is why this button is here, in order to set our baseline to 0. After the sixth standard, the all the data point has been completed, the instrument will automatically draw a straight calibration curve or calibration line. It will be straight if your standards are prepared according to good analytical practices, but if the standards are not according to the good analytical practices, so this line may have some deviation. So if you see here, this is the y-axis, we are noting the absorbance, and this is the x-axis, we are noting the concentration. So here the R-square value is very important, and in this particular case it is 0.998, which is a good approximate. It means these data points are good and we can accept this data for further calculation of our unknown concentration. So what this value means, this value can be 100% correct. If it reaches to 1, it means perfectly all the points are on the line. Here it is 0.998, it means a little bit points are deviating from the straight line, otherwise it's okay. So this R-square value should be close to 1 or 0.99, then it will be a good approximate. However, if after point the second digit is decreasing, then we can not accept that data and we have to prepare standards at once. Now after getting this data, we can save these data points, because this experiment is lengthy, so maybe some due to the load shedding, or maybe we want to save this data for further future reference in order to determine the unknown concentration. So we can save this data inside this instrument. So in order to save this data, we will press the button number 2, so the data will be saved inside. There are two options of saving the data. First option is for save inside the instrument, and second is the flash device. You can attach that flash device and store data there. And if you are using the internal storage of the instrument, so 10 files can be saved at a time. So if you select this file and then open this file, then we will get again this file which is saved. So we will directly jump to this screen, and from this screen then we will use the unknown concentration of a sample. How? If you see in the bottom of this screen, here you have seen the option of measure. So if we press this button measure and then place the unknown concentration solution in the sample compartment with the sample cuvette side, so we will press the measure, and after then we will press the start button, then we will get the unknown concentration of the solution. So if you see here, this is the unknown concentration of a solution which is measured by using the calibration curve from the standards, and here you can see the answer which is of 2 ppm. So just by pressing the measure menu and then inserting our unknown sample, we can press the start button and we can find the unknown concentration of our solution. So in this way we determine the unknown concentration by using the calibration curve or the calibration line of the standard solutions. These are the standard solution that we have prepared. This is 4 ppm solution, this is 2 ppm solution, this is 3 ppm solution, this is 4, and this is the 5 ppm solution. So all these solutions are of standard solutions, and we have obtained the calibration curve of these solutions. So now we will focus on what is the calibration curve. So as according to the instrument, on y-axis there is absorbance, on x-axis there is concentration or ppm. So in ideal condition all the data points are on a straight line. So actually if we right click on the Excel this menu, then we have an option of display equation on a chart, and when we open this equation, then this equation is actually equation of straight line, where this is the y-axis, this is the slope of this line, this is the x-axis, and this is the x-intercept. So in this particular graph, the y-axis is actually the absorbance, m is the slope of this line, whereas x is the concentration in ppm, and this c is the x intercept, which can have a value of positive or negative. For example, if this value is here, so it cuts the x-axis in a negative value, and if its value is like this, so here it is cutting the x-axis or intercepting the x-axis, and it will have a positive value. However, if for example this in this case, as the line is directly passing exactly through the origin, so the intercept value will be 0. So in this case, how the instrument actually measures the concentration, because instrument is made just only in order to determine the absorbance, how it measures concentration. So if we rearrange this equation and divide the slope of this line by absorbance, so we get the concentration or the unknown concentration of a solution. So in this way, the calibration line is actually used to determine the unknown concentration of a solution. So it means our whole analysis depends upon the standards, and how good your standards are, it will directly influence the results of your analysis. So if you have prepared standards by adopting the good analytical practices, then the answer of your unknown concentration will be acceptable, and it will be reliable, and it will be good. However, if your standards are not prepared well, then it will directly influence the results of your analysis. So the preparation of standards is the key in this whole experiment. Now there is question that, for example, you have prepared the maximum concentration of the solution of the standard, which is 5 ppm, and in case your unknown concentration is greater than the concentration, then what you will do? For example, if your solution is colored, then you will see that your unknown concentration solution is darker than this solution. So what you will do? You can perform the method of standard dilution method. In that method, what you will do, that you will take 1 ml from that unknown concentration solution and dilute it to 10 ml, or you can dilute to 100 ml, so that it can lie in the range of your standards. So then after you will perform your experiment, you will answer your unknown concentration. For example, it reaches 10 ppm, but as originally you have diluted the solution into 10 times or 100 times, then in order to give the final answer, you will multiply this with your dilution factor, and then you will actually give the final result after multiplying with the dilution factor, or multiplying with how many times you have diluted your original solution. So in this way, by adopting the method of standard dilution method, you can analyze the solution that is even higher than the highest standard that you have used in order to prepare the calibration curve. What you will do if your unknown concentration lies below the detection limit of the instrument. For example, in this particular instrument, if I say that the detection limit of this HALO DB-20 UV-Visible Spectrophotometer is 1 ppm, like it never measures any concentration below 1 ppm, and if your unknown concentration solution, by looking at it, is diluted than this, then what you will do? So in that case, you will perform the standard addition method, or you will do it by calling it, that method is called as pre-concentration method. And what you will do, for example, your solution contains approximately 0.5 ppm concentration, and this unknown concentration is below the detection limit of the instrument. So instrument measures this concentration as 0. What you will do, you will add on your own, like for example 5 ppm concentration solution in your unknown solution. Now the value total value becomes greater than the detection limit. For example, now the final value comes to 5.5 ppm. So you already know that you have added 5 ppm by yourself. So in the final answer you will deduct the added amount, and after the calculation you will give the final answer. So by using this method, which is called as standardization method or pre-consideration method, you can even measure the solutions which are below the detection limit of the instrument. And the last question is what you will do, for example, if you are using the visible spectrophotometer and your samples are not colored, then what you will do? So you will do additional step, and what you will do is that step is called as derivatization step. In derivatization step you will make your solution colored. For example, you are analyzing the iron concentration. So iron solution is usually colorless. So what you will do, you will add organic reagent. For example, you will add 110 phenanthroline. So this is the structure of 110 phenanthroline, and it is actually the organic reagent. It actually make a complex with iron, and this complex is of red color. So the colorless iron has been converted into a colored solution. So we will perform an additional step, and this step will not only be performed in your standards, and this step will be performed in your unknown concentration solution. So we will first convert the solutions into a colored solution, and then after we will use the visible range of the spectrophotometer in order to determine the unknown concentration. So this step is also called as derivatization step, and it is defined as these are the steps in order to tune the sample in order to run it in the best possible or the best possible method that is available in our instrument. So by tuning our sample, we can use the spectrophotometer or the visible spectrophotometer even for the colorless solutions. So this was all about today's lecture. I hope you have well understood this experiment, but however, if you have any confusion or question, you can ask in the comment section. Okay, thank you. Allah Hafiz.